Hello everyone, welcome you all to live session 4 of NPTEL course Fluid Flow Operations taught by Professor Sriprata Kumar Majumdar, and my name is Nagvan Sai Kumar and I am the teaching assistant for this course. Last week we have gone through fundamentals of flows where we have discussed different type of fluids like compressible fluids, invisible fluids. Okay, and this week today we'll be going through one-dimensional flow. Okay. So, but before going into one-dimensional flow, let's understand what are the basic equations of fluid flow. Okay, so we have three main important principles. That is, principle of conservation of mass flow, also known as equation of continuity or continuity equation. And then we have principle of conservation of energy, which is also known as energy equation. And then we have principle of conservation of momentum. It is called momentum equation. Okay. And apart from this, we also have a law of thermodynamic properties to analyze compressible fluids. So we have already learned about compressible fluids, right? So this is one type of fluid. Like when last week when we were discussing about different categories that we have in fluids, we also came across compressible fluids, right? So can someone tell me what is a compressible fluid? What is meant by compressible fluid? Compressible fluid is nothing but fluid with whose density changes, okay, as a function of pressure. Okay, so yeah, so we'll be using law of thermodynamics to analyze compressible fluids, and then we also have equation of state of perfect gas. This is to understand the behavior of physical properties of a gas. Okay, so we'll be going through principle of conservation of mass flow, principle of conservation of energy, and also principle of conservation of momentum in this session. Okay, so these were already discussed in the class by professor, so I'll be just going through um, all these three principles, and then we'll also be deriving a couple of equations as well. Okay, so but before that, first let's understand what is a three-dimensional, two-dimensional, and a one-dimensional flow. Okay, so this we have already studied in the last, I think we discussed it in the last session, right? Okay, so what is a three-dimensional flow? Nothing but a flow which is having velocity in all the three directions. Okay, so it has velocity in x direction, y direction, and z direction, velocity components. Okay, so you can take an example of a ball flying in the air, and okay, a ball flying in air, so it has a three-dimensional velocity. It has velocity components in all the three directions, right? Okay. So, but how do you represent a three-dimensional flow? So it has basically three components, right? So u, v, and w. Okay, so u can be written as, it has all the three dimensions, is a function of y, x, y, z, and also t, time. So it varies with time as well, right? So if it is a steady state, this will be constant. Time will be there will be no variation with time. But if it is an unsteady state, it will be varying with time. Okay. Then we have y component, which is function of again x, y, z, and t, and w as function of x, y, z, and t. Okay. And then we have two-dimensional flow. Okay. So what are the examples of two-dimensional flow? So you can take a liquid flowing between two parallel plates. Okay, so that is an example of two-dimensional flow. Again, here if you want to represent the velocities, here basically you will be velocity will be having two components, basically in x and y direction. So it can also have other components like it can have in x y direction, or it can have in x z direction, or it can have in y z directions. So it can have any of these three combinations. Okay. So for let's say if example the velocity is in velocity is having components in x and y directions. So then how do you represent? You represent as u is equal to as a function of x, y, and t as well, because if it is an unsteady state, it properties will also change with respect to time. Okay. Then we have velocity in y direction, that is function of x, y, and t again. Okay. Sorry. And then we have one-dimensional flow. So one-dimensional flow, typically you can take example of a liquid flowing in a tube in terms of average velocity. Then its velocity component can be written as u is equal to u as a function of x and t. Okay. Again, if it is a steady state, it will be constant with respect to time. But if it is unsteady state, it will be varying with time as well. Okay. So now let's understand principle of conservation of mass flow. Okay. So let's take a fluid flowing between a steam tube. Let me draw it. Let's say we have a cross section or a stream tube which is having two different cross sections. Okay, so flow is in this direction and it is coming out. Okay, so let's take section 1 which is having area of A1. So let's say this is A1 and it is flowing, and the flow is having a velocity of V1. Area is A1 and let's say this is section 1. Okay, and then we have section 2, basically cross section, and then we have, let's say this is section 2. So area is changing, so velocity will also be changing. So let's say this is V2 and area is A2. Let's also consider density as ρ1 and ρ2. Okay, so if it is some kind of a compressible fluid, because of the change in pressure, it might be compressing, right, and density might be changing. So let's say the density is ρ1 in section 1 and ρ2 in section 2. Okay, so we already described these variables. A1 is area. A1 and A2 are cross-sectional areas across section 1 and 2, and velocity V1 and V2 are velocities across cross sections or across sections 1 and 2. Okay, so now let's apply principle of conservation of mass. So if you apply principle of conservation of mass, it states that mass can neither be created nor destroyed, right? Okay, so whatever mass is entering, it should be coming out. Okay, so rate of inflow of fluid mass between section 1 and 2. So this is basically rate of inflow. This should be equal to rate of outflow plus anything that is getting accumulated between the sections, right? Input is equal to output plus accumulation. That's what we are writing here. So it will be equal to rate of output of fluid mass between section 1 and 2 plus rate of storage of fluid mass within sections 1 and 2. Okay, so that means rate of input is equal to rate of output plus accumulation. So let's say if this flow is steady state, if the flow is flowing steadily, then what happens? If the flow is steady, this becomes zero, right? Accumulation, there will not be any accumulation, right? So whatever mass that is flowing in, it will be coming out. So basically rate of storage will be zero at steady state conditions. Rate of storage will be zero. Okay, The normalized will be, that means rate of input will be equal to rate of output. So let's write dm1 by dt, that is rate of change of mass, or rate of rate of input will be equal to dm2 by dt, that is mass out. Okay. So how do you calculate mass? Mass is nothing but density into volume, right? Okay. And here we are talking about mass flow rate. Okay. So this will be volume flow rate. So how do you calculate this? Density into, how do you calculate rate of change of volume? Area into velocity, right? Okay. So same thing I'll do. Instead of mass, I'll take density into area into flow rate. Okay. So dm1 by dt will be equal to rho a1 into v1. Okay. So if you want, you can also take it as rho 1, and dm by d2, dm2 by dt will be equal to rho to a2 by, rho to a2 v2. Okay. Here v is velocity. Okay. So if you substitute them, we'll be getting rho 1 a1 v1 will be equal to rho 2 a2 v2, which is constant. That means mass rate of flow is constant. Okay. So this is the case when we are dealing with steady state flows. But when you're taking non-steady, unsteady state, so we will be having one more term, that is rate of accumulation or rate of storage, right? Because that won't be zero. Okay, so first let's this is unsteady state flow. I think I lost the internet. Am I audible enough? Okay, so for continuity equation, that is for unsteady state. So we'll take the same example. So let me just go back to the figure. Yeah. So same example. Let's do it for the case of unsteady state. So in that case, okay. So mass of fluid entering the control volume through phase AB. That is. Oh, let me draw it again. So we have two sections, right? So let's say this is AB and this is CD. That is section 1 and section 2. Okay. So same thing. This is V1. Area is going to be A1 and the velocity will be V2 and area is going to be A2. Let's say densities are also different, rho 1 and rho 2, because we might be dealing with the case of compressible fluids as well, right? So in that case, density might be changing. Okay, so now time interval is going to be delta t. So now mass of fluid entering will be equal to MIL will be equal to rho AV. Okay, that is total mass minus change of mass with time. Okay, that is going to be rho by rho L to rho AV into del L by 2 into del T. This is mass input. So this is going to be total mass, that is, or the initial mass that is entering into the fluid, and whatever mass that is changing with respect to time. This is going to be del L, length of this section, okay, or distance between these two sections. If this is dl, then rate of change of mass is going to be this. So we'll be getting dou m by dou L, right? Okay. So instead of m, we are writing rho A into V, that is anyway mass, right? So now for mass of fluid is exiting the control volume, it will be MOL is equal to rho AV. So this time this extra mass is being added to this fluid, right? So that will be plus into dou by dou L into rho AV into del L by 2 into delta T. Okay. So now how do you calculate mass difference? That is MIL minus MOL, right? Or input minus output. So this is nothing but increase in mass of the controller. So we are basically calculating accumulation part. Okay. So we just have to subtract them. We have rho A V minus dou by dou L into rho A V into del L by 2 into del T minus rho AV plus rho by rho L into rho AV into del L by 2 into delta T. Okay, so now it becomes minus dou by dou L into rho AV into del L into del T. Okay. So now increase in mass of control volume in terms of delta T will be equal to so del M will be equal to dou by dou T into rho A del L into del T. Okay. So now these two terms will be equal, right? Because both are change in mass or increase in mass of a control volume. So now rho by dou T into rho A into dou L into dou T. This should be equal to dou by dou L into rho A V into del L into del T. Okay, so if you take this to the other side, we'll be getting dou by dou T into rho A plus dou by dou L into rho A V is equal to 0. So this is the continuity equation for one-dimensional unsteady state flow. Continuity equation for one-dimensional unsteady flow. Okay. So let's look at a couple of examples based on equation of continuity or continuity equation. So first question, a pipeline tapers from 8 cm diameter to 4 cm diameter. The quantity of water flowing in the pipeline is 0.1 meter cube per second. What is the discharge and average velocity at the two sections? Okay, so we have a pipeline something like this. So initially it was having a diameter of 8 centimeters and it was tapering to a final diameter of around 4 centimeters. So this is section 1 and this is section 2. Okay, so we were also given the flow rate of water, that is 0.1 meter cube per second. We are asked to calculate discharge and average velocities at the two sections. Okay, so how are we going to do? So first let's write down all the terms that we are given. So Q is equal to 0.1 meter cube per second, right? A1 is given because diameter is given, right? So we can calculate diameter. So what is the diameter of this? Pi d square by 4, right? So pi by 4 into what is the diameter? 8 into 10 power minus 2 whole square. This is going to be area 1 and we have area 2, that is pi by 4 into 4 into 10 power minus 2 whole square. This is going to be area in meters or meter square. Okay, let's say V1 and V2 are the average velocities. Okay, at section 1 and 2. So we already learned that flow rate remains constant, right? So Q will be equal to A1 V1 into A2 V2. This is going to be constant, right, from equation of continuity. So from there we can calculate. So we know A1, A2, we also know Q. We'll be able to calculate V1 and V2, right? So V1 will be equal to Q by A1 and so let's write this first, 0.1 by pi by 4 into 8 into 10 power minus 2 whole square. Okay, so if you solve this, you will be getting value for V1. Okay, so I'm going to write directly. You can cross check this. So V1 will be equal to 20 meter per second, and similarly V2 will be Q by A2. Okay, so Q1 is again 0.1. So Q is 0.1 and A2 is pi by 4 into 10 power minus 2 whole square. Again, if you simplify this, V2 will be around 80 meter per second. So if you observe, A1 is having a higher area, right? And A2 is having a lower area. Okay, but if you observe the velocities, V1 is smaller and V2 is having a higher value, right? Because that means if area is higher, velocity will be lower, and if area is lower, velocity will be higher. Okay, because to follow the equation of continuity, when you're multiplying two terms, it should be constant, right? So that is why if one variable is higher, the other value will be smaller. Okay. So similarly, we'll also solve one more problem. Water flows in a 6 centimeter diameter pipe, with a flow rate of 0.06 meter cube per second. The pipe is reduced in diameter to 2.8 centimeters. Calculate the maximum velocity in the pipe. Also calculate the mass flux. Assume uniform velocity profiles. Okay. So same thing. Q will be equal to area into velocity. This doesn't change. Okay. So flow rate is also constant. Volumetric flow rate is constant. Q is equal to 0.06 meter cube per second. right? They are changing the diameter of the pipeline. Okay, so initially A1 will be equal to, again, pi d square by 4 into 6 into 10 power minus 2 whole square. This is going to be area 1 and this is going to be area 2, pi by 4 into 2.8 into 10 power minus 2 whole square. Okay, this is going to be area 2. We are asked to calculate average maximum velocities. So how do you do it? Same, just substitute it. Q will be equal to A1 into V1 will be equal to A2 into V2. Okay, so if we know areas, we know flow rate, volumetric flow rates, then we will be able to calculate V1 and V2, right? So V1 will be nothing but Q by A1 and V2 will be equal to Q by A2, right? So we have value of Q, we have value of A1 and A2, just substitute that, and if you do it properly, we will be getting V2 as 32.5 meter per second. Okay, and we're also asked to calculate mass flux, right? So mass flux is nothing but mass flow rate, that is density into flow rate, volumetric flow rate. So if you observe the units, density is kilogram per meter cube, right? And this is meter cube per second. So this gets cancelled out and we'll be having kg per second, which is nothing but units of mass flux. Okay, so just multiply density into volumetric flow rate, that is 1000, because we was given that water is flowing in the pipeline, right? So density of water is 1000 kg per meter cube, and flow rate is, what is the flow rate? 0.06, right? 0.06. So we'll be getting 60 kg per second as the answer. Okay. And coming to the next problem, calculate the velocity if 10 meter cube per hour of water flows through a 100 mm inside diameter pipe. If the pipe is reduced to 80 mm inside diameter, what will be the velocity? Same thing, we were given Q as 10 meter cube per hour. Okay, observe the unit, this is in R, not in seconds. And then A1 will be, we were given D1, that is 100 mm, and we were given D2 as 80 mm. Okay, so A1 will be equal to, again, pi by 4 into D square, that is 100 whole square, and then we are given A2, that is pi by 4 into 80 whole square. Okay, so again Q1 is equal to A1 V1 into A2 V2, right? So we just need to calculate the value of V2. So V2 will be equal to Q, that is 10 by, what is the area? Pi by 4 into 80 whole square. So we'll be getting in meter per hour. Okay, so you can convert it into whichever units you want, meter per second or meter per hour, because they did not mention anything, right? So you can, but basically we'll be denoting it in meter per second, right? So it is better to convert it into meter per second. Okay. Yeah, and one more thing, this is in mm, right? So we have to convert it into meters, that is 10 power minus 3 whole square. Again into 10 power minus 3, this will be in meter square. So here we will be having 10 power minus 3 in whole square. Okay. So final answer V2 will be 0.55 meter per second. This is in seconds. Okay. But you will be getting in hours because this is given as meter per hour, right? So you'll be getting in hours, you have to convert it into seconds. Okay. So now coming to continuity equation, let's derive continuity equation for a three-dimensional flow. Okay. So let's Let's consider a fluid element which is having lengths of dx, dy, and this is dz. Okay, in x, y, and z directions. Okay, so these are the lengths of fluid element, length, breadth, and height of fluid elements in x, y, z directions. And let's say fluid is flowing in this direction. Okay, this is A, B, and we have C and D. This is E, F, G, and H. Okay, so fluid is flowing in direction, and let's say fluid is having components in x, y, z, and z directions. So let's say U, V, and W are components, velocity components in x, y, and z directions. Okay, and let's say rho is the density, mass density of a fluid element at a particular, in this particular fluid element. So mass of fluid entering the phase A, B, C, that is inlet through this phase, will be equal to mass density into, that is density into velocity into, and that too in x direction, because this is flowing in x direction, right? So in x direction, velocity in x direction into area of ABCD, phase ABCD through which it is flowing. Okay, so this will be equal to rho into U into del Y into del Z. Okay, this is the area of this phase, right? Okay, and then similarly, mass of fluid leaving the phase EFGH will be equal to rho U into dou Y dou Z. Along with this, we'll also be having a small fraction. Okay, because if it's an unsteady state, obviously there will be some other extra fluid that is being exiting, right? So that is a fractional amount of fluid that is being exiting the fluid stream. Okay, so now rate of increase in mass in x direction will be outflow minus inflow, or accumulation basically. Rate of accumulation or rate of increase in mass in x direction. So this is nothing but outflow minus inflow. Okay, so this will be rho U dy dx plus rho U dy dx by dou x into dx minus rho U dy dz, right? So this is also z. Okay, so both these terms gets cancelled out, and we'll be left with dou rho U dx dy and dz by d dou x. Okay, so similarly in y direction, rate of increase in mass will be equal to dou rho v dx dy dz by dou y. Okay, so here we are using v, and because v is the velocity component in y direction, right? Okay, and in z direction, mass will be dou rho w dx dy dz by dou z. Okay. So now total mass increase which is coming out like total mass that is accumulated, total rate of increase in mass will be equal to combination of all the three, right? You just have to add all the three in x, y and z directions. So if you add them and take out the common variables, we will be having dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z into dx, dy and dz, which is equal to 0. Okay. So now from law of conservation of mass, total rate of increase in mass should always be 0, right? Okay. So that is why we are equating it to 0. Okay. So for compressible fluids, rho will not be constant, right? So that is why we will be having for compressible fluid, this is compressible fluids, rho is not constant. So we have dou rho u by dou x plus dou rho v by dou y plus dou rho w by rho z, which is equal to 0. And for incompressible fluids, rho is constant, right? Okay, so in that case, rho can be taken out. So we'll be left with dou u by dou x plus dou v by dou y plus dou w by dou z, which is equal to 0. This is nothing but equation of continuity for three-dimensional flow. Equation of, or continuity equation, you can say it as continuity equation. You can call it as continuity equation. Continuity equation for three-dimensional flow. Okay. So now let's apply this to two-dimensional flows. Okay. So we have the equation for three-dimensional flow, right? So we'll be able to reduce it to two-dimensional as well, right? So let's see how to reduce it. So when a fluid is flowing in a two-dimensional, or if the flow is a two-dimensional flow, that is in xy plane. So let's take it in xy plane. We can also have it in yz and xz planes as well. So for time being, let's consider the flow is in xy plane. Okay. So then the last term of the equation of continuity for 3D flow will be 0, or it will not be existing. So this term, it will not be existing for a two-dimensional flow. So hence the equation of continuity for a two-dimensional incompressible fluid will become dou u by dou x plus dou v by dou y is equal to 0. This is for incompressible fluids, and for compressible fluids it will be dou rho u by dou x plus dou rho v by dou y is equal to 0. This is for compressible fluids. Okay, let's do an example. So let's say if the velocity distribution for a 2D incompressible fluid, 2D incompressible fluid, velocity distribution for a two-dimensional incompressible fluid is given by u is equal to ln x square y square minus 4 ln xt, and v is given as 2y by x plus 4 ln xt. Okay, so now we have to check if this velocity distribution is following equation of continuity or not. Okay, so for a two-dimensional incompressible flow, what is the equation of continuity? Dou u by dou x plus dou u by dou y, so dou v by dou y should be equal to 0. Okay, if this follows, then these equations will follow the equation of continuity. Okay, so first let's do dou u by dou x. So dou u by dou x is nothing but, so let's just substitute u here. We will be getting dou by dou x into ln x square y square minus 4 ln xt. Okay, so this gives us 1 by x square y square, and for x square it will be 2x, right? Okay, minus 4 by xt. Okay, and for v it will be 2y by x plus 4 ln xt. So this is going to give us 2 by x plus, well, this is going to be 0. This is going to be 2 by x. Okay. Yes or no? Sorry, we have one more term, right? Okay, sorry. Okay, this is going to be minus 2 by x. Okay, so add them up. Dou u by dou x plus dou v by dou y. If you add them up, we will be getting minus 2 by x plus 2 by x. This is 0. Okay. So that means the equation of continuity is satisfied. Okay, it follows the equation of continuity. Okay, earlier I did so this differentiation was wrong. So now we will be getting minus 2 by x. If you differentiate that, we will be getting minus 2 by x. Okay. And similarly, let's take another example where u and v are given as 2x square plus 2xy, and v is given as 2yz square plus 3z square. Okay, so this is a three-dimensional flow, three-dimensional incompressible flow. So we are supposed to find w. Okay, so what is the equation for three-dimensional flow? Du by dx plus dv by dou v by dou y plus dou w by dou z will be equal to 0, right? So just substitute, find the integral, and then we'll be able to find z component. So can someone do it and tell me the answer? What is what is w? Can someone solve it and let me know the answer? So what is dou u by dou x? It will be dou by dou x into 2x square plus 2xy, right? Okay, so that is going to give us 4x plus 2y, right? Okay, and then we have to find dou v by dou y. This is going to be 2y square into 2y into z square plus 3z square. Okay, this is going to give us 3z square, right? Sorry, this is going to give us 2z square. Okay, so now just substitute in this equation. So we have 4x plus 2y plus 2z square plus dou w by dou z is equal to 0. So now dou w by dou z is equal to minus 4x minus 2y minus 2z square. Okay, so now w, so just integrate it, we will be having minus 4xz minus 2yz minus 2 by 3 z cube plus integral constant c. Okay, so if you are given any initial conditions, we will be able to calculate c as well, right? Okay, so this is how we will be able to calculate the other component of velocity. Okay, so let's see one more example. So here we were given two-dimensional flow again, two-dimensional incompressible flow. Okay, so u is given as minus ky by x square plus y square, and v is given as k x by x square plus y square, and we are asked to calculate value of x. So same thing, dou u by dou u by dou x plus dou u by dou v by dou y should be equal to 0, right? So do the partial integration and it should be equal to 0. So if you calculate dou u by dou x, it will be 2x ky by x square plus y square whole square. Okay, dou u by dou x, and if you calculate dou v by dou y, it will be minus 2y into kx by x square plus y square whole square. Okay, so now add them up, dou u by dou x plus dou v by dou y, which is 2x y into k by x square plus y square whole square minus 2xy into k by x square plus y square whole square. This should be equal to 0, right? So this will be possible. When will this be possible? It will be, if you solve this, you will be getting k as 1. Okay, so let's see one more problem. Same, we were given uh, incompressible flow. That is u is equal to x power 4 plus 3 z power 4, and w as y power 4 minus 3 yz, and we are asked to calculate v. Okay, so same thing, dou u by dou x will be equal to, dou u by dou x plus dou v by dou y plus dou w by dou z. This should be equal to 0. Okay, calculate dou u by dou x. This will be equal to 4x cube plus this will be 4x cube, and dou w by dou z will be equal to minus 3y. Okay, so substitute them in this equation. We'll be getting 4x cube plus dou v by dou y minus 3y. This will be 0. Okay, so take them to the other side. Dou v by dou y will be equal to 3y minus 4x cube. Okay, so if you integrate this, we'll be getting v is equal to 3 by 2y square minus minus 4 x cube into y plus constant. Okay, so again, if you are given any initial conditions or some sort of conditions, we will be able to solve for C as well. Okay, so now coming to conservation of fluid energy. Okay, so basically every fluid will have three type of energies. One is potential, one is kinetic energy, the second one is potential energy, and then we also have pressure energy. Okay, so let's see how this works. Let's take three examples. Let's say we have a fluid in three similar kind of containers to a similar height. Okay, so in one case, water is drawn from a height h naught. Okay, so we have a pipeline, and this is the height of water. Okay, so if water is being ejected from here, okay, it can have any number of turns. If water is ejected from here, we will be having both potential energy and kinetic energy as well. Okay, because it is not exactly equal to height of water, right? So here we will be having pressure energy. Okay, because pressure exerted from water, we have pressure energy. Okay, we also have kinetic energy because of flow of water. As this is flowing with certain velocity, it will be having kinetic energy as well, and then it will also have potential energy as well. Okay, because it is at a certain elevation. Okay, but in second case, let's say we are drawing water from the same height, but we are ejecting from somewhere which is almost equal to the height of this water level. So in this case, we only have kinetic energy. Okay, because this is almost equal to the water, right? So this is a continuous fluid, right? So they are at the same height. So pressure force will be 0, and kinetic energy will also potential energy will also be 0. So only kinetic energy has to push this, right? So it will be very low. But let's take an example where you are having at the very bottom. Okay, here you have higher amount of pressure energy, higher amount of potential energy, and also higher amount of kinetic energy as well. Okay, so basically sum of all the forces, this pressure, kinetic and potential energy, will be constant. Okay, so that is what we will be using to derive Bernoulli's equation. Sum of all the energies is going to be constant. So Daniel Bernoulli He's a Swiss mathematician and a physicist. So he was the one who formulated this equation, Bernoulli's equation. So that is why he named Bernoulli equation. So he basically uh, Bernoulli equation basically states that sum of all the energies is constant. Okay. So let's take a streamline element, which is nothing but an element which follows the direction of fluid velocity. Okay. Let's say just flowing with the velocity v. Okay. And this obviously will have a mass component rho g dA into ds. We'll also come to these variables as well. So ds is length. Okay. dA is the area of this cylinder. And this is the value dz, that is the high distance between or vertical distance between these two ends. Okay. And we are doing it for a uniform flow. Okay. So let's say this angle is theta. Okay. So now net pressure acting on the element will be F net will be equal to PdA, that is pressure force that is acting, minus P plus dou P by dou S into ds into dA. Okay. That is change in pressure force minus weight that is acting, weight component. So this is acting downward, right? So we'll also be having component in this direction. So it will be opposite to the pressure force. So minus rho into dA into ds into g cos theta. Okay. So if you simplify this, we'll be getting minus dou P by dou S into ds into dA minus rho into dA into ds into g cos theta. Okay. So as per Newton's law, force is nothing but mass into acceleration, right? As per Newton's law, force is equal to mass into acceleration, right? So this should be equal to rho into dA into ds into dv by dt. This is acceleration and this is mass. Okay. So let's say this is equation 1 and this is equation 2. So from 1 and 2, if we equate them, we have dv by dt is equal to minus 1 by rho into dou P by dou S minus g cos theta. Okay. So velocity may change with both position and time, right? So it's so in one dimensional flow, it is therefore becomes function of both distance and time. Okay. So v is v of s here is function of both displacement and or position and time. So dv will be equal to dou v by dou t into dt plus dou v by dou s into ds. Okay. So acceleration can be written as, your main concern is to calculate acceleration, right? So acceleration is then written as dv by dt, which is equal to dou v by dou t plus dou v by dou s into ds by dt, which is nothing but dou v by dou t plus v into, because this is v, right? into dou v by dou s. Okay, this gives us acceleration. Okay, so from here, if you calculate this cos theta, okay, that will be equal to dz by ds, right? Okay, this is the angle, so it will give us cos theta will give us dz by ds, right? Okay, so let's give equation numbers as well. This is 1, 2, and this becomes 3, this is 4, and this is 5. Okay, let's say this is equation 6. Okay, so equation 3 becomes, so from, let's take equation 3 and equation 5. Okay, that is these two equations. We can write dou v by dou t plus v into dou v by dou s is equal to minus 1 by rho into dou p by dou s minus g into dou z by dou s. Let's say this is equation 7. Okay, so for steady state, this will be 0, right? Dou v by dou t will be equal to 0. So then this becomes v into dou v by dou s is equal to minus 1 by rho into dou p by dou s minus g into dz by ds. Okay, so this is called Euler equation. Euler's equation. Euler's equation of motion for one-dimensional non-viscous fluid. Okay. So now let's say this is equation 8. Let's say this is equation 8. So now if you, okay, we don't have space, I guess. So if you integrate this equation with respect to s to obtain relationship between points, infinite distance between the streamline, finite distance between streamline, you will be getting v square by 2 plus rho integral dp by rho plus gz is equal to constant. So if you integrate this equation, okay, and for incompressible fluids, rho is constant, right? So then this equation becomes v square by 2 plus p by rho plus gz is equal to constant. This is a Bernoulli's equation. Potential head, kinetic head plus pressure head plus potential head will be constant. So if you multiply them by rho, you will be getting rho v square by 2 plus p plus rho gz, that is equal to constant. Okay. of coming to energy equation for non-uniform flow. Okay. Okay. So in a real fluid flow across a large cross-section area, the velocity distribution will be non-uniform, right? Okay, because of friction losses and all these things, it will be non-uniform. So the kinetic energy per unit weight of a fluid transferred across this section is greater than the calculated value, which will be done by average velocity. It will be actually higher than that. So that is why true kinetic energy will always be expressed as Ke true will be expressed as alpha into v square by 2g. Okay, where alpha is the correction factor, kinetic energy correction factor. Okay, and value of alpha will vary from 1.03 to 1.6, sorry, 1.06 for turbulent flow, and this varies, this will be equal to 2 for laminar flow. Okay, so if you take this into account, then the Bernoulli's equation will become alpha into v1 square by 2g plus p1 by rho g plus z1 is equal to rho v2 square by 2g plus p2 by rho g plus z2. Okay, this is for non-uniform flow. So coming to limitations, because we were assuming few things, right? So Bernoulli's theorem also has few limitations. So velocity is in Bernoulli's equation we consider velocity as uniform over the section. So if velocity is non-uniform, we cannot apply this equation again. And we also assume fluid is non-viscous, that is frictional losses will be zero, but in real situations there will be frictional losses, right? So again in those conditions Bernoulli's equation will be invalid, and we are also assuming flow to be steady state. Again, if it's not steady, we will not be able to do it. We are assuming that flow is along the streamline and flow is homogeneous and incompressible, and we also assume that gravity and except gravity and pressure forces, there are no other forces or energies that are involved. But if any of these things are changing, or let's say if any of these things are violated, then we'll not be able to apply this Bernoulli's theorem or Bernoulli's equation. Okay. So coming to dynamic, static and stagnation pressure. So if streamline is horizontal, okay, so in case of flow, let's take an example. Let's say if the flow is in a straight line. So if you connect a manometer, in this case you will observe that the pressure difference is same. Okay, or basically you can say potential energy is same in this case. Okay, so this can be omitted from Bernoulli's equation. So we can have rho v square by 2 plus ps is equal to pt, where this is dynamic pressure because this keeps on changing with velocity. This is dynamic pressure, this is static pressure, and this is total or stagnation pressure. Okay, so in this case we'll be calculating, this is going to give us the total head. Okay, and if we have okay, so this is fine, dynamic, static and stagnation pressures. So let's take an example. A liquid is flowing in a horizontal pipe of a flow rate. In a horizontal pipe at a flow rate of 0.05 meter cube per second. The length of the pipe is 200 meters. Its center is 3 meters above the bottom line. The pipe tapers from 0.3 meters to 0.3 diameters to 0.2 meters. If the pressure at longer end of the pipeline is 98100 Newton per meter square, calculate the pressure at the other end. Neglect the losses. There is no head exerted by any external machines. So we have to apply Bernoulli's equation. So what is Bernoulli's equation? V1 square by 2g plus P1 by rho g plus Z1 plus He, that is losses due to or any other external heads, will be equal to V2 square by 2g plus P2 by rho g plus Z2 plus H2, that is frictional losses. So these two are 0, right? So we just have to use this equation. So we can neglect these two terms, that is loss side. So we were given that diameter is changing, right? So it is initially 0.3 and changed to 0.2. So we know the flow rate Q is equal to 0.05 meter cube per second. We were given D1 as 0.3 and D2 as 0.2. So from here we can calculate V1 as Q by A1 and V2 as Q by A2. So if we do it, we'll be getting V1 as 0.707 meter per second and V2 as 1.592 meter per second. Okay. We are also given P1 as 98100, right? Just substitute them, we'll be getting the final answer. Okay. So if you substitute them and if you calculate properly, we are supposed to get P2 as 99115 Newton per meter square. Okay. So coming to applications of Bernoulli's equation. So it can be applied in practical cases. So we'll be using venturimeter, flow nozzle, orifice plate, and also pitot tube. So you can apply these. You can apply this Bernoulli's equation in all these equipments, all these discharge measuring equipments. That is venturimeter, flow nozzle, orifice plate, and pitot tube. And also it will be able to help solve the problems of flow under slice gate, which is used in the construction of an open channel. And it can also be applied in radial flow and also in free vortex motions. Okay. So now coming to linear momentum. So this is the third principle, right? Principle of conservation of momentum. So we learned about conservation of mass, that is continuity equation. Then we also learned about the conservation of energy, that is derivation of Bernoulli's equation. And now we'll learn about conservation of momentum. If you have any doubts until now, you can ask me. You can post them in the chat box or unmute yourself and ask me. Okay, so whenever you are, let's take two real life examples. One, a ball which is thrown, okay, horizontally with a velocity v, and a car which is moving with the same velocity v. Okay, one is a ball moving with velocity v and the car moving with the same velocity v. Okay, so you will be able to stop this ball using a glove, right? Okay, using a simple glove you can catch this or you can stop this. But whereas coming to car, you will not be able to stop this car simply by holding it or simply by stopping with your bare hand. Okay, why? This is because mass also plays an important role, or it is because of something called momentum. Okay, it's not just because of velocity, it's something called momentum. So momentum is mass multiplied by velocity. Okay, so this gives us momentum. So if the mass is high, momentum, let's say in these two cases, velocity is same, but mass is changing, right? It is many times, car is many times heavier than ball, right? Okay, so that is why you will not be able to. That is the momentum of car will be very high, whereas momentum of ball will be small when compared to this. That is why you will be able to stop the ball using gloves, but whereas you will not be able to stop this car just by your hands. Okay, this is called linear momentum. Okay, so by Newton's second law of motion, the change per unit time, in the momentum of a body is equal to the force acting on the body. Okay, that is increase in momentum is equal to momentum going out minus momentum going in. So according to Newton's second law, force is nothing but the change in momentum of the body. F is equal to mv2 minus mv1 by, just a second, by time. This is Newton's second law. Okay. So coming to applications of equation of motion, you can apply it for a force of jet. Force of jet is water jet, and it can also be applied in cases where there is sudden loss because of expansion in the pipe. You can also apply it for jet pump and also for efficiency of a propeller. Okay, so let's see the case of force of a jet at rest. Okay, so let's consider two-dimensional jet that is striking a inclined plate. So let's say this is a pipeline from which jet is coming out, water jet. So and it is striking a flat inclined plane. Okay, whenever it is striking it, it will be okay. So let's say this is having an angle of theta with the horizontal. Okay, this is horizontal, the pipe is horizontal, or the jet is horizontal and the pipe is having an inclination of theta. Okay, so let's say this is the control volume that we are choosing. So this is Q and this is Q1 and this is Q2. There is water flowing upward and downward directions. So Q will be equal to Q1 plus Q2, right? Okay. So whenever this is hitting this inclined wall, when the water is hitting the inclined wall, it will be exerting a force. It will be exerting certain force on this, right? So this will be again having Fx and Fy as its component, x and y component, horizontal and vertical components. Okay. So now let's try to find a total force. So if the velocity of the fluid of the jet turns out to be 0 after it has struck to the flat surface at v sin theta, then F will be equal to rho into Q into v sin theta. Okay. So Fx will be equal to F sin theta, that is rho Q v into sin square theta, and Fy will be equal to F cos theta, that is rho Q v sin theta cos theta. Okay. And rho Q cos theta will be equal to rho q1v minus rho q2v, which is q1 minus q2. So q1 will be equal to q1 plus cos theta by 2, q2 will be equal to q into 1 minus cos theta by 2. Okay. So this is again same thing when the body is moving in the same direction as the fluid. So let's say if body is moving with a velocity v, then how do you calculate the force? Okay, so this is already discussed again. This was also discussed, jet pump was also discussed, efficiency was also discussed in the class. Okay, so I'm going to skip this part. But if you have any doubts in this section, you can unmute yourself and ask me, or post them in the chat box as well. If you don't have any doubts, we can move on to the problem session. If you have any doubts, you can unmute yourself and ask me. If not, we can move on to this problem session. We must have already gone through the lectures, right? So, be it from the videos that you saw, like from the professor's recorded lectures, you can ask me, or maybe in this current session, if you have any doubts, you can ask me. I'll try to answer them. Okay, so if you don't have any doubts, then we can move on to the problem session. Okay, so the continuity equation is based on the principle of the conservation of mass, the conservation of linear momentum, the conservation of angular momentum, the conservation of energy. So, which of these following equations are correct? Which of the following principle is used for continuity equation? That is equation conservation of mass, option A. So coming to second question, two pipes of diameter D and 2D respectively converge into a third pipe of diameter 4D. If the velocities of an incompressible fluid are V1 and V2 in the two pipelines respectively, what would be the velocity of the fluid in the third pipeline? So how do you do this? So we are basically having let's do it in a different way. Okay, this is having diameter of D, and this is 2D, and this is having a diameter of 4D. Okay, and velocity in this first pipeline is V1 and this is V2. So what would be the velocity here? That is V3. So the fluid which is flowing into this, okay, this is coming from first pipeline and second pipeline, right? So it is a combination. So let's say this is having a flow rate of Q1, Q2 and this is Q3. So Q3 is nothing but Q1 plus Q2, right? Okay. So what would be the value of Q3? That is area, that is A3 into V3, right? Okay. So similarly Q1 will be A1 into V1 and Q2 will be A2 into V2. Okay. So how do you calculate A1, A2, A3? So we're already given diameters, right? So for A3 it will be V3 into, what is A3? pi by 4 into d square. What is value of d? 4d whole square. That will be equal to v1. And what is the area of a1? What is the value of a1? Pi by 4 into d square plus v2 into pi by 4 into 2d whole square, right? So just simplify this. Will be, so cancel out pi by 4. Okay, so we'll be having v3 into 16d square will be equal to v1 into d square plus v2 into 4d square, right? So cancel out d square and you'll be left with v3 is equal to v1 plus 4 v2 by 16. Okay, so this is going to be the velocity in the third pipeline. Okay, so we just because whatever fluid is coming from v1 and v2 or pipeline 1 and 2, that should be entering into pipeline 3, right? So q3 will be equal to q1 plus q2. So from there we just substituted value of q3, q1 and q2. Then we just simplified it and we got v3 value. Okay. So coming to third question, what is the correct form of continuity equation for two-dimensional steady flow of a compressible fluid, where u is x component, y component and z component. Y is the coordinate. Okay, rho is the density. Okay, this is for a two-dimensional equation and it is for a compressible fluid. So for compressible fluid, density term will always be there, right? Okay, because density will also keep changing. So for two-dimensional flow, what is the equation? Dou into rho u by rho x plus dou rho v by dou y is equal to 0. So which of these options matches to this? That is option B, right? Okay. So coming to fourth question. In a two-dimensional steady flow fluid field, the velocity of an incompressible fluid along the x-axis is given by, so we were given velocity distribution u is equal to kx square plus ky square, where k is constant. If v is equal to 0 at y is equal to 0, find velocity in y direction. That is, we want to find value of v or expression for v. So this is a two-dimensional flow, right? So what is, for two-dimensional flow, what is the equation of continuity? Dou u by dou x plus dou v by dou y is equal to 0, right? So what is value of dou u by dou x? It will be dou by dou x into kx square plus ky square is equal, so this becomes 2x into k. Okay, so substitute dou u by dou x plus dou v by dou y is equal to 0, right? The substitute value of dou u by dou x, it will be 2x into k plus dou v by dou y is equal to 0. This becomes dou v by dou y is equal to minus 2kx. Okay, dou v by dou y is minus 2kx, right? So just integrate this, we will be getting v is equal to minus 2kxy plus c. Okay, but we're also given a condition, right, that v is equal to 0 at y is equal to 0. So if you substitute this, we will be getting c as 0. Okay, that means 0 is equal to 0 plus c. C will be 0. So that means v is equal to minus 2kxy. Okay. So moving on to fifth question. A fluid flows at a rate of 150 meter cube per hour inside a pipe of diameter 0.5 meter. Find the velocity of the fluid if the diameter is reduced to 0.25 meter for the same flow rate. Okay, so we already solved this type of problems, right? Q is given as 150 meter cube per hour. Okay, so we were given d1, that is 0.5 meter. We were given d2, that is 0.25 meter. Okay, we'll be able to calculate a1, right? A1 will be equal to pi by 4 into 0.5 whole square, and a2 will be pi by 4 into 0.25 whole square, right? So now q will be equal to a1 v1, that is a2 v2. Okay, so we can directly do it. A2 is pi by 4 into 0.25 whole square into v2, which would be equal to q, that is 150 meter cube per hour. So if you solve this, v2 will be, you'll be getting some value. So this is in hour. We should be converting into second as well, because all the options are given in meter per second. So this you don't have to convert because it's already in meters. So you just have to convert hours into seconds. So if you do it properly, answer would be 0.848 meter per second. Okay. So coming to sixth question, in a two-dimensional steady flow field, the velocity of an incompressible fluid along the x-axis and y-axis are we were given, so I think A and B are missing. So U is given as AXY plus BY, and V is given as CY square. Okay. So these are the velocity distributions in a two-dimensional steady-state flow. So we were asked to find condition for ABC such a way that they will be following equation of continuity. So again, what is the equation of continuity for two-dimensional flow? Dou U by dou X plus dou U by dou V by dou Y should be equal to 0. Okay. So what is value of dou U by dou X? That is dou by dou X into AXY plus BY. This will be equal to A. And what is dou V by dou Y? It will be dou by dou Y into CY square. This will give us 2YC. So if you substitute them in this equation, we will be getting A plus 2 A plus 2 YC should be equal to 0, right? That would be option C, but we were not given any other conditions, right? Okay, so like I think I have to cross check this. So option is C. It is not given. So I'll cross check this and I'll get back to you. Okay. So coming to seventh question, which of the following conditions are not necessary for application of Bernoulli's equation? That is inviscid fluid, incompressible flow, steady flow, none of these above. Which of these following conditions are not necessary? Okay, we need all the conditions for Bernoulli's equation. So option D, it is none of the above, is correct. So coming to question 8, which of the following relations is correct? Stagnation pressure is equal to dynamic pressure plus static pressure. Static pressure is equal to dynamic pressure plus stagnation pressure. Dynamic pressure is equal to static pressure plus stagnation pressure. None of the above. So we just discussed this, right? Stagnation pressure is equal to dynamic pressure plus static pressure. Stagnation pressure is also called as total pressure. Okay. Assuming that Bernoulli's equation is valid in the case of a horizontal streamline, what would happen to the pressure if the velocity is doubled? Okay. So just write down the equation. Bernoulli's equation is V square by 2g plus P by rho g, P1 by rho g plus Z1 is equal to V2 square by 2g plus P2 by rho g plus Z2. So it is mentioned that this is a horizontal streamline, so Z will be same, so they'll be get cancelled out. So here velocity is double, right? So now V2 is equal to 2V1. Okay. So if you substitute that, V1 square by 2g plus P1 by rho g will be equal to 2V1 square by 2g plus P2 by rho g. So this will give us V1 square by 2g plus P1 by rho g is equal to 4 V1 square by 2g plus P2 by rho g. So if you take the other side, we will be getting P2 by rho g will be equal to P1 by rho g minus 3 V1 square by 2g. Okay, so that means if the pressure is double, if the velocity is double, pressure will be reduced. So because P1 is, let's say it's a fixed quantity, you are reducing some, or if you are subtracting a certain value from this pressure rate, or P1 by rho g, you are subtracting certain value. That means P2 will be less than P1, right? Okay, so that means pressure gets reduced. Option A. So coming to 10th question, according to Bernoulli's equation, the total head in a horizontal nozzle can be expressed as a sum of the velocity head and the pressure head, velocity head, pressure head, and the potential head, the pressure head and the potential head, none of the above. So total head in a horizontal nozzle. So if it is a horizontal nozzle, then there will not be any potential head, right? Because V by 2g, V square by 2g plus P by rho g plus Z1 is constant, right? But if it is a horizontal nozzle, then there will not be any change in height rate. So Z1 will be equal to Z2. So Z will be cancelled out. So Bernoulli's equation can be expressed in terms of velocity head and pressure head. That is option A. Okay. So if you have any doubts, you can ask me. If not, we can end this session. You can either unmute yourself and ask me, or post them in the chat box as well. Any doubts? Any doubts in the problems, or any doubts? If you don't have any doubts, then we can end this session. Okay. Thank you, everyone. Thank you for attending the session. Let's meet on next Tuesday.